Euclidean geometry. Euclid is often called the father of geometry, not because he invented it, but because his geometry textbook is the oldest one that we have existence in the Western world today. You can see all 13 of his books online. They've been translated and put on the internet for free. Euclid believed that each part of geometry should be based on previously proven parts. However, we have to start somewhere. So he suggested 4 undefined terms and 5 basic axioms. Everything else in Euclidean geometry is based upon these 9 items. The 5th axiom, called the parallel postulate, has been very controversial. It's more complex than the other 4 axioms, and many mathematicians tried to prove it using the first 4. Failure to do so led to the discovery of non-Euclidean geometries. The 4 undefined terms are point, line, plane, and space. Notice that a point is 0 dimension, a line has 1 dimension, a plane has 2 dimensions, and space has 3 dimensions. The 5 axioms talk about lines. Number 1, a straight line can be drawn between any 2 points. We would call this a line segment. Number 2 says that we can extend that line segment infinitely in both directions. Number 3, a circle can be drawn with a center placed anywhere and any size radius. Number 4, all right angles are equal to each other. If we accept this, then we can determine the length and comparison of other angles by adding and subtracting to the right angle. Number 5, the parallel postulate. Given a line and a point not on the line, only one line can be drawn through the point parallel to the line. That's a little bit convoluted, so here's a picture. We have line L and point P. We can draw one line through point P that is parallel to the line L. That's the pink line. Notice if we draw any other line, like the red one, through point P, that eventually it will cross line L. It can't be parallel if it crosses. There were many mathematicians who worked on the 5th postulate, trying to prove that it could be derived from the other 4. Saccheri first tried to use a proof by contradiction. He uncovered 2 new types of geometry. Gauss, Bolyai, Lobachevsky, and Riemann were all mathematicians that also tried to prove it and also developed the 2 geometries discovered by Saccheri. The parallel postulate was not able to be proved, even by contradiction. But if we think about this, it can help us learn about the 2 new types of non-Euclidean geometry. A proof by contradiction assumes that the original statement is false, so the postulate is false, and then tries to prove that the opposite is true. In our rigorous proof, we would use valid geometrical steps supported by properties, definitions, theorems, and corollaries. And then at the end, when we end up with a blatantly false statement, then the only thing that we can decide is our error was at the beginning. So what is the opposite or the negation of the parallel postulate? Well, the opposite of one parallel line would be either no parallel lines or more than one parallel line. We'll consider these 2 cases separately. Case 1, given a line and a point not on the line, there are no lines through the point that are parallel to the given line. And case 2, given a line and a point not on the line, there are infinitely many lines through the point parallel to the given line. With the original case and these 2, we've covered all possibilities. Spherical geometry is the case that led to having no parallel lines. This geometry takes place on the surface of a sphere rather than on a Euclidean plane like we're used to. The best example of the application of spherical geometry is navigating around the Earth, usually done by airplanes but also by boats. This is where we come up with the concept of a great circle. Case 2 leads to hyperbolic geometry, the case where there are infinitely many parallel lines to a given point. This geometry is sort of the opposite of spherical geometry. If we took that sphere, put a hole in it, and turned it wrong side out, we might see something that would look like a saddle. However, this geometry surface goes infinitely in all directions. Spherical geometry is based on a plane. 4 of the axioms hold in this geometry. Only the 5th axiom is different. So let's check it out. A straight line, or a line segment, remember, can be drawn between any 2 points. Well, pick any 2 points on the surface of the sphere and draw a straight line between them. Now we have to learn about what we mean by straight. In the English language, straight means it doesn't have a kink or a curve, something we could draw that is straight, like a straight line. But in geometry, a straight line simply means a line that is the shortest distance between 2 points. So our 2 points on the surface, we can identify a shortest distance path and draw it. That is what we call a line. We can extend this line segment infinitely long. It will go around the sphere and connect back to itself and just trace over and over and over, but it will be infinitely long. Can we draw a circle with any center and radius? Well, sure. Pick a center anywhere you want. Pick Berlin, Germany. Okay. How big do you want your circle to be? 25 miles? Well, draw a circle where every point on the circle is 25 miles from Berlin. Latitude lines are what we think of as circles in spherical geometry. Are all right angles equal to each other? Well, we can draw right angles on the surface of a sphere. For example, the intersection of longitude and latitude lines. So we can determine that they're equal to each other, and thereby all angles can be defined from that. But there are no parallel lines in spherical geometry. You might say, well, I can draw 2 parallel lines, but remember, parallel lines are defined as never intersecting. And a line in spherical geometry is defined as a great circle, which can only be drawn around the fattest part of the sphere, always dividing the sphere into 2 equal parts. So we cannot find 2 parallel lines or 2 great circles that don't intersect each other. All great circles intersect in 2 places. What about polygons in spherical geometry? How many of them behave normally in Euclidean, and how many are different? For example, let's take a triangle. Choose 3 points somewhere on the sphere. Can we connect them with straight lines or great circles? Yes, we use the first axiom to make each side. So triangles do exist, but they look like they have fatter angles than normal. We know a sum of the triangles in Euclidean geometry is 180 degrees. Sorry, sum of the angles. Is this true in spherical geometry? Well, let's pick a very specific triangle. Let's put 2 of the points on the equator and the 3rd point on the North Pole. Wait a minute, 3 right angles? How could that be? We could find a triangle where the North Pole had a 90-degree angle and the perpendicular to the equator both have 90-degree angles. The sum of angles for this triangle is 270 degrees. And if we spread the legs of the triangle even further apart, we'd have a bigger sum. In spherical geometry, the triangle angle sum is always greater than 180 degrees. What about a square? Can we draw a square on a sphere that doesn't even have parallel lines? Well, let's see. What is a square? A square is a regular quadrilateral, meaning it has 4 equal sides and 4 equal angles. So if we pick 4 points on our sphere so that those points are equal distance from their adjacent sides and that the angles are the same, we've drawn a square, as in the picture. This is a regular quadrilateral, but it doesn't have the same properties as a square in Euclidean geometry. The sides are not parallel and the angles are not 90 degrees. Hyperbolic geometry exists on a negatively curved infinite surface. Think about a horse saddle with the edges going off into infinity, and every point on the surface acting as if it were the saddle's center, curving up in one direction and down in the other direction, kind of a reflexive point. The first 4 axioms also hold in hyperbolic geometry, but the 5th axiom does not. Let's check and make sure. Can we draw a line segment between any 2 points? Sure. Pick any 2 anywhere on the saddle. You'll be able to draw a shortest path or a straight line between them. Can we extend that finite line segment infinitely in both directions? Well, remember, the saddle goes infinitely in all directions on the edge, and so we can extend the line infinitely in both directions. Can we draw a circle? Sure. Pick any point you want. Pick a radius. Draw a circle. It might look like a large warm pancake that melted on the saddle surface, but it will still be a circle. Can we draw right angles? Sure. They'll be perpendicular at their intersection, but they'll look like they're curving away from each other as we get further away from the intersection. And the fifth postulate or axiom? Parallel lines never exist, remember? So draw any line you want on the saddle. Now choose a point on one side of the line. Draw a line that does not cross your original line. Draw another line through this point. You can draw as many as you want because there are infinitely many possible lines that do not intersect your first line but still go through that point. There are many parallel lines. There are some models for hyperbolic geometry different from the saddle idea. The pseudosphere is a trumpet-shaped surface that extends infinitely at both the pointed end and the edge of the bell. The flare of the bell shows the negative curvature that we talked about with the saddle. This model is difficult to imagine going to infinity, but it does on both ends. The Poincaré disk is named after a French mathematician. He designed this as a hyperbolic model that looks like it's just the interior of a circle without any edge because the edge is infinitely far away. The dotted line on the model shows that this surface goes to infinity in all directions. And imagine that you're looking straight down the throat of the pseudosphere, so the center of this circle is also infinite. Another model can be made actually in 3D space. This can be knitted or crocheted and is often called a hyperbolic doily. The edge of this doily becomes more curly as it approaches the infinite edge. Choose 2 points on the edge of this model and find the shortest path between them. Unless these are straight across from each other, the shortest path is going to be a pathway closer to the center and not along the frilly edge. And I'm going to go back because we have a video. See if this works. Here's my hyperbolic doily. I pick 2 points straight across from each other and draw a straight line of shortest distance. But if I pick 2 points that are closer to each other on the edge, what's the shortest distance? Is it going up and over? Or is it tracking in towards the center and over to the other point? It's straight because it's the shortest distance, even though to us it looks like it's curved. So lines in hyperbolic space on the hyperbolic doily are always going to curve towards the center unless they're exactly through the center. There are 2 kinds of lines in hyperbolic geometry. We've seen the one that's on the diameter of the disk. That looks straight like we're used to. An example here is line segment CD. Actually line CD because it goes infinitely. Look at line AB. Since those 2 points are not directly across from each other, we sort of take a swerve towards the center to avoid those hills and mountains that would be a longer travel space. Then we have line EF, because the points are closer or appear closer on the edge, but remember the edge is infinitely long. The curve is not quite so far towards the center. Which of these 3 lines are parallel? In other words, which of these 3 lines don't intersect? Notice that line AB is parallel to line EF. Now that goes against the grain because we're used to Euclidean geometry, but remember parallel just means they don't cross, ever. Consider a triangle in hyperbolic geometry. Pick some points on the disk and connect them with straight lines. Remember the straight lines here are going to be the curved sides. We find a triangle, but now it has extra skinny angles. In fact, the sum of the angles of a triangle is always less than 180 degrees in hyperbolic geometry. It's kind of like they're shrunk in. Consider a square. Carefully pick 4 points, connect them with straight lines, and create a regular quadrilateral with congruent sides and congruent angles. It's not a square by definition, or it is a square by definition, but the sides are not parallel, and the sum of the angles is no longer 360. Let's look at more properties of hyperbolic geometry. A circle drawn on a globe can have any length radius, but the circumference gets interesting. Think about this. Put the center of your circle at the North Pole. Have your radius be half the circumference of the Earth. Then that will fall on the South Pole. Now what do you have? You have a wonderful circle with area, the surface of the Earth, but its circumference is 0 because it's a point. The area of triangles also gets tricky. Usually we think of the Euclidean area of a triangle as base times height divided by 2. But this has three different answers depending on which side of the triangle you use as